I'm Bitwise Assembly, and today we're continuing the pipe testing series with another prioritization method, attempting to visualize headlift disconnects, raising the flow rate for all recycling methods, and finally building recycling setups outside of the lab. A quick recap of the recycling combinations and their rates. Recycling rate listed here is the ratio of waste liquid to total required liquid for a process step. Where the recycling point is varies based upon the setup, but every setup has one, unless the setup ends in sinking the liquid into an unrelated process. Jumping over to a new to me method, the valve headlift disconnect, which was suggested by Reddit user Stucco, and is probably the prioritization method most likely to be used by accident. Looking at the flow in the valve may be confusing, as the valve is a small fluid buffer that allows unrestricted flow in and out of its output. The flow restrictions are applied to the input side of the valve. The UI flow rate in this case shows the flow in and out of the output end of the valve, since we can see no flow in the pipe before it. If we look at the head lift in each section, we can confirm the valve prevents backpropagation of machine head lift, creating a head lift differential which likely encourages reverse flow into the valve. I attempted to perform the same visualization on the buffer head lift disconnect, but as you can see, it did not go well. The inclusion of multiple buffers or vertical empty pipes causes undesired flow, which in turn raise the fluid level in the buffer, breaking the Mark II setup instantly and bringing the Mark I setup uncomfortably close to failure. Without the head lift meters, the fill level stays low. In my testing, the industrial fluid buffer appears to be more stable and consistently outperforms the smaller buffer. To get a better picture of how the prioritization methods work over a range of flows, we at least need a second data point. So I present to you 500 flow rate test stands. Each test stand is a closed loop of packagers and unpackagers simulating a factory with waste liquid. The source unpackagers are set to 120, 600 in total, and the production building packagers are set to 100 each, 500 in total. The wastewater unpackagers are adjusted to determine the maximum rate. The layouts shown here are some common ways of connecting the waste pipe and will act as our baselines for comparison when we look at prioritization methods. The bottom tap does not perform well with Mark II pipes and worse at higher flow rates. Still better than the baseline, but not by much. Deploying this with multiple returns and Mark I pipes works better, which we will look at later. The VIP junction, a crowd favorite, maintains a strong prioritization even at higher flow rates. The valve head lift disconnect loses some prioritization at higher flow rates. It is interesting that the VIP junction, valve, and buffer head lift disconnects all scored about the same in the 500 flow rate tests. The industrial buffer head lift disconnect was the only prioritization method that was not affected by the flow, maintaining its 100% prioritization regardless of pipe model or flow. The high pipe return was my solution of choice in my early playthroughs. Trying to find the exact failure point was difficult. The failure point is somewhere between 85 and 90% recycle rate. The vertical fluid columns in the 500 flow rate test stand caused extra flow between the columns, which improved the recycle rate over the 100 flow rate test stand. The bottom tap in a distributed setup is my current preferred solution. With a recycling rate of 98%, this setup handles all but one recipe and lands in a solid second at this flow rate. If you're going to use this setup yourself, it is critical that the pipes connected to the vertical junction are all Mark I. Now that we've covered every prioritization method that I know about at both low and high flow rates, it's time to leave the test benches and test some real setups. Here are the 4 setups that we'll test with the sloppy aluminum and electrode aluminum scrap recipes, which is a 70% recycle rate. Welcome back to my son's world. We're on the cliffs south of the Rocky Desert starting location, where there is a pure bauxite node. We are using a spare oil node for the petroleum coke and pumping water up from directly below. The sloppy alumina and electrode aluminum scrap combo is a difficult recipe to handle without deploying a prioritization method or strategy, which is why I chose it. The recipe information shown here will be the same for all 4 builds. The way I approach recipes that have an intermediate product is to normalize the recipe by setting the rate of the intermediate product to the same on both machines, which in this case means underclocking the sloppy alumina to 75%. Once you have a normalized pair or module, you can simplify the requirements of the recipe and reduce the math down to just the number of modules required, which for this setup is 8. I know this means building more machines than is needed, but it does reduce the math and planning. For the direct recycling build, I'm using the bottom tap prioritization on each module, making it a distributed setup, and building 8 modules that use up the 1200 bauxite. Note the parentheses around the value is for the alumina solution. This will carry over to the other builds, where the machines are not side by side. Since this is just test builds, we are sinking the aluminum scrap. Direct recycling, if deployed properly, can be used for any size factory, and is in fact the only type that I have used in my playthroughs. So let's change that and build a 2-level cascade, also called keeping your wastewater separate from your source water. Here we have the 2-level cascade. The machines are separated into 2 groups: main, which receives only fresh water, and recycle C1, which runs on the wastewater from main group and itself. The ratio of recycle C1 group's wastewater to the main's wastewater is the same as the direct recycling rate. The benefit in this version is the main group can act like a smart valve by setting up the main group as the lowest priority of source materials. With the added group comes extra math. On the spreadsheet, I have listed the percent of total production for each group and recipe. I've also provided the results as a fraction for added precision. For this build, we're still using the same modules from the direct recycling, where the sloppy alumina is running at 3/4 the target rate of the module. Since the recycle rate is still 70%, a prioritization method is required to prevent system failure when not running at 100%. To prioritize the C1 wastewater, I used the valve headlift disconnect on the main group's wastewater line, but any of the methods that scored over 70% would work. I used 2 return lines for the C1 wastewater, as the combined flow in these lines is 588, which is above my comfort level for a single Mark II pipe. To test recovery of this setup, I intentionally caused system failures by cutting the C1 wastewater lines and ran the system until failure. The lines were then replaced and the setup fully recovered. The test without a prioritization method failed to recover. Let's review the recipes and the recycle rates for the Level 2 Cascade. Let's move on to the 3-level Cascade, which is described on page 14 of the pipeline manual, link in the description. The Level 3 Cascade added an additional group in the wastewater loop. The benefit there is we apply the recycling rate twice, which squares the recycling rate. With the addition of a second recycling group brings with it additional math. I've expanded the spreadsheet for the additional group, maintaining fractions for precision. The main here is identical to the two-level cascade, but the recycling rate drops to 49%, which based upon my own testing would require a prioritization method even when feeding the wastewater opposed. So I was quite surprised when the system recovered without one. Notice I have the percentages here listed as fractions. This is because you can type them in this way to maintain the full floating point precision beyond what you can see in the UI. Viewing this value in a save editor, you will see up to 20 decimal places. Recycle group C2 runs only using the wastewater from C1. C2's wastewater is used in combination with main's wastewater to run C1. As part of the testing with these setups, I intentionally caused failures to ensure the system can recover. To test this setup, the waste return pipe segment was removed and replaced after the system failed. It took the system a full hour to fully recover, including a prioritization method would have sped up that recovery. Let's look at the recycling rates for the three-level cascade. As we get to four-level cascade, I should state that this level of complexity is really only beneficial to megafactories. With three steps in the recycling loop, we now need to cube the direct recycling rate to get this setup's recycling rate. Adding another group means even more math. At this level, it is important to keep the results as fractions, since most of the answers contain repeating decimals. I did all of the calculations by hand while waiting for the high flow rate test stands to stabilize. I have a high confidence it's all correct, but feel free to check my work. The main group here, as you've probably guessed, is the same as the level 2 Cascade main group, as the percentage here is only affected by the recycling rate of the recipe. With the effective recycling rate being lower than the level 2 Cascade, it was not a surprise that it did not require a prioritization method to pass the recovery test. To test the recovery from backup, I cut the C3 waste line until failure and replaced it for recovery. The full recovery was about 30 minutes for this setup. One last look at the recycling rates for the level 4 Cascade. For those wondering about the effects of slooping, it makes the setups super complicated, as the recycling rate also increases, especially if you sloop both stages in the setup, since you can get up to 4 times the recycling rate, which could be handy if you want to make a water source in the middle of nowhere, or sloop a few modules to reduce or eliminate the need for source water. So I'm probably not going to expand on the subject more unless Coffee Stain updates the fluid mechanics. As it is, this video took way longer than expected, since I started it before Fixmas. Thank you for waiting, and thank you for watching. The blueprints used in this video can be found in the channel links.